This section is on the decreasing time algorithm. So one good first attempt to find a priority list that will work well is to maybe try to prioritize the jobs that take longer above the shorter jobs, saving the shorter jobs for last. And you may even do this in everyday life. Maybe you have a bunch of homework assignments or projects all to do in one night, and maybe for some people you might think, oh, it'll be easier or I'll feel better if I get the longer time consuming tasks done first, and then I'll be finishing up some of the shorter tasks. And of course, some people think the opposite way. But anyway, with this, we're going to prioritize longer time consuming tasks first. So the decreasing time priority list, it's just a list. And we take the times of the tasks and put them in decreasing order. And then the decreasing time algorithm is just using that list to create a schedule. Here's a more advanced example. We're not going to work this whole thing out, but just to kind of illustrate, we take all the tasks, and this one there's 15 tasks, and we just order those from greatest amount of time to least amount of time, hoping to get the least amount of time total in the end, also minimizing idle time as well. So here's the solution to that problem. We get a finishing time of 42 hours with two processors, and it looks like we have about 14 hours of idle time. So not too bad considering all the tasks and how complex the problem is. But next we'll start out with one that's a little more at the difficulty that we're going to be doing in class. So here's an example similar to the last section of notes, and it might even be the exact same diagraph. But this time what I've done is reordered the priority list so that task C, the longest task, is prioritized first, while task D, the shortest task, is prioritized last. So it looks that C, A, and B are all ready from the start. Okay, I've color coded these again, so C will be red. So C is going to take, now we have two processors, so 7 hours, so we take C, I'm going to shade all the way up here to 7 hours. Okay, so C has been being executed right now, so we'll give task A to worker 2, and task A is going to take 6 hours. Alright, and task A is now in execution. And at hour 6, task A is completed, and task C is still being worked on. Okay, so the only thing we can do is give task B away to worker 2 at this point. And task B takes 5 hours to complete, so from 6 it's going to be all the way up here to 11. Okay, so now we can say that B is in execution. So while B is being worked on, worker 1 finishes task C at 7 hours. Now C is the prerequisite for E, so now after C has been completed, we can say that E is ready. So we'll give E to worker 1. And E takes 5 hours as well. So from there, that's 7 hours plus 5, so it's going to go all the way up here to 12. Alright, as E is in execution, notice at hour 11, task B is complete. So now that A and B are complete, task D is now ready. And we can give task D, that's a 2-hour task, we can give that to worker 1. So 11, 12, and 13. Okay, so now task D is in execution. At hour 12, task E becomes complete. There's nothing else to do, so worker 1 is just going to have to be idle for 1 hour, and then we'll finish up our project here. Remember, D is completed at hour 13, so we'll say fin equals 13. And again, always just good to include the amount of idle time, so we'll say 1 hour idle. That's pretty good. So we did a pretty good job minimizing the amount of total time as well as the idle time, only 1 hour of idle time there. There are 2 more examples to follow this, and if you're taking the notes along with this, I would like you to try those on your own, and then we'll go over those in class. One thing I did forget to mention is that notice that B and E, those tasks, have the same amount of time, and we could have just as easily used put E in front of B in the priority list. And the only thing is, it may have come out with a different answer. It may not have. So just when you get a tie like that, just choose one and stick with it.